There is a mountain range in southeastern Australia that most people think they understand. They know it as a ski destination. They know it as the source of the Snowy Mountains hydroelectric scheme, one of the great engineering projects of 20th century Australia, the network of tunnels and dams and power stations that redirected the rivers of the high country to generate electricity and irrigate the agricultural land of the interior. They know it as the setting of the Man from Snowy River. They know it as the place where you go in winter if you want to ski, and in summer if you want to walk among alpine wildflowers at the highest elevations accessible by road in Australia. What almost none of them know is what scientists have found when they looked at the Snowy Mountains not as a landscape but as a geological system, a biological archive, a hydrological network, and a record of human presence that extends back far further than the European pastoral history that most Australians associate with the high country. Because when researchers looked carefully, the Snowy Mountains turned out to be carrying secrets that none of the disciplines involved expected to find. Findings that individually revised what was understood in their respective fields. Findings that, when assembled together, produce a picture of this landscape that is significantly more complex, more ancient, and more scientifically important than the ski resort version of the Snowy Mountains suggests. This is that picture. If you are new here, this channel covers Australian history, science, and country that most people were never properly taught. Subscribe now and let me know in the comments below what you thought you knew about the Snowy Mountains before watching this video today. Let us start with the geology. Because the foundation of everything else that has been found here begins with what the mountains are made of and how they came to be. The Snowy Mountains are part of the Australian Alps, the highest section of the Great Dividing Range that runs along the eastern edge of the continent from Queensland to Victoria. The highest point of the range and of the entire Australian continent is Mount Kosciuszko at 2,228 meters above sea level. By the standards of mountain ranges on other continents, this is modest. The Alps of Europe reach more than 4,000 meters. The Himalayas exceed 8,000. By global standards, the Snowy Mountains are hills. By Australian standards, they are extraordinary. And the rock they are made of is significantly older and more geologically complex than their modest elevation suggests. The granite that forms the core of the Snowy Mountains was emplaced as molten magma deep underground during the Silurian and Devonian periods, between roughly 400 and 420 million years ago, during a major episode of mountain building that geologists call the Lachlan orogeny. The Lachlan orogeny was caused by the collision and accretion of island arcs and oceanic crust onto the eastern margin of what was then the Australian part of the Gondwana supercontinent, a process that generated intense deformation, metamorphism, and igneous activity across the region. The mountains that formed during the Lachlan orogeny were, at their peak, significantly taller than what remains today. They have been eroding continuously for 400 million years. What remains is their root, the granite core that was once buried at depth, now exposed at the surface as the overlying rock has been removed by hundreds of millions of years of weathering. This is the same deep geological story that appears at Uluru and in the Black Forest. Ancient mountains reduced to their crystalline cores by the incomprehensible slow work of geological time. But what the recent geological surveys of the Snowy Mountains have revealed goes beyond this broad picture in ways that surprise the researchers who conducted them. Deep seismic surveys and magnetotelluric imaging conducted across the Lachlan Fold Belt, the broader geological province of which the Snowy Mountains form the highest part, have documented a level of structural complexity in the deep crust beneath this region that was not apparent from surface geology. The basement beneath the Snowy Mountains is not the simple granite batholith that the surface geology suggests. It is a composite of multiple distinct geological terrains, fragments of ancient oceanic crust, island arc material, and continental basement that were assembled during the Lachlan orogeny by the collision and accretion process. These distinct fragments retain different physical and chemical properties in the deep crust, and the boundaries between them, known as terrain boundaries, are zones of structural complexity that extend from the surface to depths of 20 kilometers or more. The terrain boundaries beneath the Snowy Mountains are zones of elevated fluid activity. Fluids moving along these deep structural boundaries carry heat and dissolved minerals upward through the crust, contributing to a geothermal environment in the deep crust that is more active than the surface geology of a quiet, stable, ancient mountain range suggests. The implications of this deep structural complexity have only recently begun to be assessed in detail, and they connect to findings from other research disciplines working in the same landscape in ways that the researchers involved did not initially anticipate. Now let us talk about the water. Because the hydrology of the Snowy Mountains is where the engineering story that most Australians know about connects to a scientific story that most Australians have never been told. The Snowy Mountains hydroelectric scheme, constructed between 1949 and 1974, is one of the largest and most complex civil engineering projects ever undertaken in Australia. It consists of 16 major dams, 7 power stations, a pumping station, 145 kilometers of tunnel, and 80 kilometers of aqueducts, redirecting the waters of the Snowy River and its tributaries westward through the mountains to irrigate the riverina agricultural region and generate electricity for the national grid. The scheme transformed the hydrology of the mountains. Rivers that had flowed east to the coast were partially redirected west through the mountains. Water levels in the high country lakes and reservoirs that form the scheme's storage system were managed to optimize power generation rather than to reflect natural hydrological cycles. What the scientific research conducted in and around the Snowy scheme over the last 3 decades has revealed is that the scheme's transformation of the mountain hydrology has had consequences that the engineers who designed it could not have fully anticipated, because they did not have access to the scientific understanding of the natural system that subsequent research has produced. The natural hydrology of the Snowy Mountains before the scheme was not simply the rivers flowing downhill. It was a system of extraordinary biological complexity, in which the flows of specific rivers at specific times of year, the timing and volume of snowmelt, the temperature cycles of high country streams, and the chemical composition of the water at different points in the drainage network all played roles in sustaining biological communities that had evolved in precise relationship to those conditions over millions of years. The Snowy Mountains are the headwaters of 3 major river systems. The Murray and the Murrumbidgee flow west and north, draining into the Murray-Darling Basin, the largest river system in Australia. The Snowy River flows east and south to the coast. These 3 drainage systems, originating within a few kilometers of each other at the top of the range, supply water to a vast area of southeastern Australia and ultimately to the ecology of the Murray-Darling system, which is one of the most ecologically significant river networks in the country. The biology that depends on those river flows, from the platypus in the high country streams to the native fish in the lowland rivers to the wetland ecosystems of the Murray Mouth in South Australia, is connected through the hydrology of the Snowy Mountains in ways that the pre-scheme ecology had been expressing for millions of years. The scientific assessment of what the scheme did to that connected biological system, conducted with increasing sophistication as the ecological research methods available to researchers improved across the decades of the scheme's operation, has produced findings that have been central to one of the most significant environmental policy debates in Australian history. The finding that the scheme's reduction of flows in the Snowy River, which was reduced to as little as 1% of its natural flow in some sections after diversion, had produced severe ecological degradation of the river and its estuary, was established by research published in the 1990s and early 2000s and led to political commitments to restore flows to the Snowy River as a condition of the scheme's corporatization. The process of implementing those flow commitments and measuring their ecological effects has itself become a significant area of scientific investigation that has produced findings about the resilience of river ecosystems and the timescales of ecological recovery that are relevant far beyond the Snowy Mountains specifically. Now let us talk about the biology. Because the biological findings from the Snowy Mountains in the last 2 decades are the ones that have produced the greatest surprise. The Snowy Mountains contain the largest area of alpine and subalpine habitat in Australia. Above the treeline, which sits at around 1,800 meters in this part of the range, the vegetation is an open landscape of snow gum woodland giving way to alpine heathland, feldmark, and the treeless tops. This environment is cold, wind-exposed, frost-prone, and seasonally snow-covered. By Australian ecological standards it is extreme. By global alpine standards it is mild, but the biological communities it supports are unique because they have evolved in isolation from comparable environments on other continents. The alpine ash and snow gum forests of the subalpine zone, and the alpine herb fields and grasslands above them support communities of plants, insects, birds, and mammals that include significant numbers of species found nowhere else. The Mountain Pygmy-possum, Burmese parvis, is perhaps the best known of these endemics. a small marsupial that was known only from fossil material and was believed to be extinct before a living individual was found in a ski lodge at Mount Hotham in 1966. The rediscovery of the mountain pygmy-possum from fossil-only knowledge is, like the woolly pine discovery, one of those findings that demonstrates how incomplete the known biological record can be and how much can be preserved in refugia that scientific survey has not reached. The mountain pygmy-possum lives in the boulder fields of the snowy mountains during summer and hibernates beneath the snow in winter, its body temperature dropping close to ambient as it enters a state of torpor. Its survival through the alpine winter depends on sufficient snow cover to insulate it from the extreme cold above the snow surface, and on the availability of the Bogong moth, which migrates to the high country in summer in enormous numbers and provides the high-fat food source the possums require to build the fat reserves that sustain them through hibernation. Both of these dependencies, snow cover and Bogong moth availability, have been identified by researchers as being under pressure from climate change. The research documenting the decline of the mountain pygmy-possum population in the snowy mountains, and the ecological research connecting that decline to reduced snow cover and changes in the Bogong moth migration, has been among the most cited evidence in Australian discussions of the ecological impacts of climate change on alpine species. But the mountain pygmy-possum story, significant as it is not the most unexpected biological finding from the snowy mountains in recent years. That distinction belongs to the research on the soil biology of the alpine zone. Soil biology is not a glamorous field. It does not attract the public attention that discoveries of large animals or dramatic landscapes generate. But the research on the microbial communities in the soils of the snowy mountains alpine zone, conducted by teams from the Australian National University and the University of New South Wales over the last 15 years, has produced findings that have significance well beyond the snowy mountains. The alpine soils of the snowy mountains contain microbial communities of extraordinary diversity and of specific functional characteristics that are not found in comparable alpine soils elsewhere in the world. The microorganisms in these soils, bacteria, archaea, and fungi operating at the base of the alpine food web, include lineages that have adapted to the specific conditions of the Australian alpine environment, conditions that differ from alpine environments in the northern hemisphere in ways that reflect the continent's long isolation and its unique geological and biological history. The functional diversity of these microbial communities, the variety of chemical and biological processes they perform in the soil, has been found by the research to be significantly higher than would be predicted from the relatively simple appearance of the alpine vegetation above the soil surface. The microbes are doing things in the soil that the surface ecosystem depends on in ways that are only now being characterized. The nitrogen cycling performed by specific bacterial communities in the alpine soils, the decomposition of organic material by fungal networks, the interactions between soil microbes and the roots of alpine plants that allow those plants to extract nutrients from a cold, nutrient-poor environment. All of these are more complex and more ecologically significant than the simple visual impression of the alpine zone conveys. This research has direct implications for understanding how the alpine zone will respond to climate change, because the soil microbial communities perform the biological processes that the ecosystem depends on, and those processes are sensitive to the temperature and moisture conditions that climate change is altering. Understanding how the microbial communities respond to changing conditions is critical to predicting how the entire alpine ecosystem will respond. Now let us talk about the human history. Because the snowy mountains have been occupied by people for far longer than the pastoral history of the high country suggests, and the archaeological research of recent decades has produced findings that extend and complicate the picture of indigenous use of the alpine zone. The Ngarigo people are the traditional custodians of the snowy mountains. Their country encompasses the high plains and the mountain valleys, and their relationship with this landscape extends back across the full period of human presence in southeastern Australia, a period that the archaeological record now places at a minimum of 40,000 years and possibly significantly longer. The archaeological evidence of Ngarigo and predecessor occupation of the snowy mountains has been recovered from rock shelters and open sites across the range at various elevations. The most significant findings have come from sites that document the seasonal use of the high country in ways that required the maintenance of detailed knowledge about when and where specific resources were available. The Bogong moth migration, which brings enormous numbers of these high-calorie moths to the granite boulder fields of the high country each summer, was a resource that Aboriginal people from across a wide area of southeastern Australia traveled to the mountains to exploit. The Bogong moths aggregate in the cool, dark crevices of the granite boulder fields in their millions during the summer months, and their fat-rich bodies provided a food source of exceptional nutritional value that attracted gatherings of people from surrounding regions. The archaeology of these Bogong moth gathering sites, documented by researchers including Dr. Josephine Flood and more recently by teams from the Australian National University, has revealed evidence of repeated, intensive use of specific high country locations across extended periods of time. The accumulated evidence from some sites documents use spanning thousands of years, with charcoal from cooking hearths and grinding stones used to process moths, creating a record of gatherings that were regular, organized, and socially significant enough to draw people from considerable distances. The Bogong moth gatherings in the Snowy Mountains were not simply subsistence activities. The accounts of early European observers who witnessed the final years of traditional gathering describe large intergroup meetings that combined food collection with ceremony, trade, dispute resolution, and the maintenance of social and kinship relationships between groups whose territories were separated by the distances of the surrounding lowlands. This is a picture of the high country as a gathering place of continental significance, a location whose seasonal resources created the conditions for meetings that sustained the social fabric of a broad region of southeastern Australia across thousands of years of occupation. The Ngarigo and their predecessors knew the Snowy Mountains in a depth of detail that the European pastoral and engineering history of the region has not matched. Their seasonal movements through the landscape, the knowledge encoded in their understanding of the Bogong moth migration, the snow patterns, the plant resources, and the water sources of the high country, represent a body of applied ecological knowledge built on thousands of years of direct experience. The research conducted in recent years in collaboration with Ngarigo knowledge holders has begun to recover and document aspects of that knowledge in ways that connect it to the scientific findings from geology, hydrology, and biology. The connections that emerge from those conversations between traditional knowledge and scientific research consistently reveal that the Ngarigo understanding of the high country landscape is more accurate and more detailed than any comparable body of scientific knowledge produced by the much shorter history of European scientific investigation. This is the pattern that appears at every significant Australian site where the effort has been made to bring traditional knowledge and scientific research into genuine dialogue. The people who have been here longest know the most. Now let us bring the full picture together. The Snowy Mountains are carrying in their geology, their hydrology, their biology, and their human history, a set of records that extends across multiple time scales. 400 million years of geological history in the granite of their core. The hydrological connections of a river system that sustains life across an enormous area of southeastern Australia. A biological community of alpine endemics that includes species thought extinct and soil microbial communities of unexpected diversity and function. And a human history of seasonal gathering and cultural significance that extends back at least 40,000 years in a landscape that the European engineering achievement in its midst has transformed in ways still being assessed. Each of these dimensions, studied individually by the research disciplines that have approached them, has produced findings that revised what was previously understood in that discipline. Brought together in a single account, they describe a landscape that is doing far more than its reputation as a ski resort and an engineering achievement suggests. The mountains are old. Their biology is complex and under pressure. Their water connects a vast area of the continent in ways that the engineering of the 20th century altered and that the ecological restoration efforts of the 21st century are trying to partially reverse. And the people who understood them most deeply carried that understanding for tens of thousands of years before the first ski lodge was built or the first tunnel was bored through the granite. The Snowy Mountains look like they are mostly about winter sports and hydroelectricity from the outside. From the inside, from the soil up, from the deep crust to the alpine summit, they are something significantly older and more layered than that. And scientists with better tools than any previous generation are still finding out what those layers contain. If this changed how you think about the Snowy Mountains, leave a comment below and subscribe for more Australian history and science that most people were never properly taught.